Hi everyone, in this video we are going to continue the problem of isentropic compression of real gas. In the previous video we have derived the equation for enthalpy changes as well as entropy changes. First let me draw a diagram. So this is compression. In this case inlet temperature was 350 Kelvin, inlet pressure was 50 kilopascal, outlet pressure was 600 kilopascal. The outlet temperature is 395.188 Kelvin that we have calculated in the previous problem. Here we are going to calculate the changes in enthalpy. I have already explained about the changes in entropy, that is 0, because this process is an isentropic compression. And in case of enthalpy, in the previous video we have derived an equation dH equal to Cp dt plus V minus T del V over del T at constant P into dP. In the previous video we have derived enthalpy as a function of temperature and pressure. Here we are going to insert those values. Before that, let me first derive del V over del T at constant P, and here the equation of state P V plus AT over P equal to RT, and I am writing this equation in terms of V as a function of pressure and temperature. That would be RT upon P minus AT over P. This would be the equation of V. If I want to calculate this term, then I can take the differentiation over LHS as well as RHS, del V over del T at constant P, that is equal to R upon P minus A upon P. The reason is we are taking the differentiation with respect to temperature, keeping pressure constant, so R upon P will be constant. The derivative of T, that is 1. Here also A upon P, that is constant. Derivative of T with respect to temperature, that is 1. This is a value of R upon del V over del T at constant pressure. I am going to put these two values in this equation. It would be V equal to, that is RT over P minus AT upon P minus this into T. So these both terms will be multiplied by T. So this is again RT upon P plus AT upon P over dP, and this would be cancelled. So ultimate equation is Cp dt. Don't think that this is an ideal gas. You can't say, if any case, if dH equal to Cp data, we can't assume this is an ideal gas, because this gas is real, and how this would be different from the problem of an ideal gas. Here the temperature is different. So temperature we got is something 395.188 Kelvin. Earlier the temperature was constant or different value. Here I can integrate this equation dH equal to Cp dt, and this would be delta H equal to Cp delta T, and here in our case delta H equal to 7 by 2 into R, 395.188 minus 350 Kelvin, and I can put the value of R 8.314 joule per mole. The final answer would be 1314.926 joule per mole. This would be changes in enthalpy. This would be different from the changes in enthalpy for an ideal gas, and this is the application of this equation. Students think that why they have derived those equation enthalpy, entropy as a function of temperature and pressure. There are so many equations you can derive enthalpy or entropy or Gibbs free energy or Helmholtz free energy as a function of temperature or pressure, as a function of temperature, volume, anything. You can derive any property as a function of other two variables based on the application. Ultimately, this is the application of this equation to solve this type of problem. We are going to solve one more problem. The statement is prove that triple product rule is true for an ideal gas. Any ideal gas can be written as a PV equal to RT. If I am considering three variables P, V and T, then if I apply triple product rule, then it would be del P over del V at constant T, del V over del T at constant P and del T over del P at constant V equal to -1. I have to prove this equation is true. Let me derive each partial derivative, then we can multiply and we can prove that that is equal to -1. First derivative, it is del P over del V. So, I am converting this equation V equal to RT upon V and taking the derivative of P with respect to V, keeping temperature constant. This is constant RT and derivative of 1 upon V, that is minus 1 upon V square, V raised to -1, that is -1 upon V square. So, this would be the answer. For second derivative, I am converting this equation V equal to RT upon P and taking the derivative with respect to temperature, keeping pressure constant. On RHS, pressure is constant R upon P and the derivative of T with respect to temperature, that is 1. For the third derivative, I can convert this equation T equal to P V upon R and I can take the derivative del T over del P, keeping V constant, and here on RHS V is constant, R is also constant, V upon R and derivative of P, that is 1. From these three derivatives, if I put the values of all three derivatives in this equation, then it would be minus RT upon V square into R upon P into V upon R equal to, I am going to prove, okay. Here R would be cancelled and one V will be cancelled. So, this is minus RT upon PV. But what is RT upon PV? From this equation RT upon PV, this is equal to 1. So, this is minus 1. So, the triple product rule is true for an ideal gas. We are going to solve one more problem. The statement is for van der Waals gas, the multiplication of these two partial derivatives equal to blank and the options are given A, B, C, D. Choose the correct one. In this case, we have to solve this problem. There are two ways to solve this problem. The first way is del P over del V at constant temperature. For van der Waals gas, we know the van der Waals equation of state. P plus something, V minus B equal to RT. We can consider this equation to calculate these two derivatives, that is the one way, and that will be little complex if we calculate the two derivatives and multiply, but we know triple product rule is true for any equation of state. I can add the third derivative here, del P over del V at constant temperature, del V over del T at constant P and del T over del P at constant volume, that is equal to -1. This is true for any real gas or any ideal gas for any equation of state, and from this equation these two equal to, I can consider -1 upon del T over del P at constant volume. So, this is, you can select anyone, calculating two derivatives, then multiply and you can get the answer. Otherwise, simply -1 upon only one derivative. So, I am going to opt for this way, del T over del P. Here T I can write this equation T equal to P plus A upon V square, V minus B upon R. This is one equation, T as a function of something, and I want to calculate derivative del T over del P, keeping volume constant. So, this 1 upon R is constant, and I can use the chain differentiation rule, keeping one constant V minus B, taking the derivative of this one. This is again constant A upon V square, but derivative of P, that would be 1, and keeping the other term constant. So, I am going to keeping P plus A upon V square and taking the derivative of these two, V minus B. V is constant as well as B is constant. So, the derivative of this term would be 0, keeping P plus A upon V square constant and taking the derivative of this with respect to pressure, that is 0. So, this term would be 0 and this would be V minus B upon R, and if you put this value in this equation, then it would be minus 1 upon V minus B upon R. So, ultimately this is R upon B minus V. So, this is correct option. Thanks for watching this video. Thank you very much.